identify chiral and achiral molecules in each of the following pairs. Okay, yeah, we need to identify in each pair which one is chiral, which is not chiral or achiral. Okay, yeah, how to identify that? This representation is called flying wedge representation. Flying wedge representation. In this representation, this center is the carbon atom. Now that carbon is connected with 4 different groups, right? See, here I have OH group, here hydrogen, here bromine, here methyl group. Therefore, this carbon is a chiral carbon. Am I right? This carbon is a chiral carbon, right? Whenever you have single chiral carbon, students, keep this in mind. In a molecule, right? Whenever a molecule contains single chiral carbon, the molecule must be chiral molecule. Yes, this is a chiral molecule. Right? Now, see the second one. In the second one, yes, here we have carbon. This here we have hydrogen. Here we have methyl group. But here, these 2 atoms are same. Therefore, this carbon is not a chiral carbon. Okay, when we can say a carbon is chiral carbon, right? Only if all the 4 groups are different. Right? So in this case, these 2 are same. Therefore, this is not a chiral molecule. So this is achiral molecule. Okay, achiral or achiral molecule. Right? This is how you must identify. Now, see the second question. Second question. 2 pairs of compounds are given. We need to identify which one is chiral and which one is achiral. Okay, the simplest way is to identify chiral carbon. Okay, so here this is the flying wedge. This OH group is in front of you. This hydrogen is behind the paper, and these bonds are in the plane of the paper. That's the meaning. Now you just see here we have methyl group, right? This carbon has methyl group. Methyl group means 3 hydrogen, so it cannot be chiral. This carbon has 2 hydrogen, CH2. Here we have CH2, here we have CH3. So definitely these 3 carbons cannot be chiral, and this methyl group cannot be chiral. So we have to focus only on this carbon now. Okay, so in this carbon we have 1 hydrogen, 1 OH group, and this side we have methyl group, and this side we have propyl group. See, all the 4 groups are different. Am I right? Am I right, student?
Yes, sir.
Yeah. So all the 4 groups are different. Therefore, this carbon is chiral carbon. Okay, so we have only 1 chiral carbon. Whenever molecule contain only 1 chiral carbon, the molecule must be a chiral molecule. The molecule must be a chiral molecule. If you have more than 1 chiral carbon, then you have to check whether the mirror image, okay, the molecule and its mirror image are non-superimposable or not. That you have to check. Okay, if a molecule contains single chiral carbon, nope. Okay, you need not worry about anything. Directly you can say the molecule is chiral molecule. Okay, now see here in this molecule, see I am going to focus on this carbon because this is CH2, this is CH3. So here we have 2 hydrogen, we have 3 hydrogen, so it cannot be chiral. Similarly, this is CH2, this is CH3. So these 2 cannot be chiral. So we have to focus only on this carbon. In this carbon, we have 1 hydrogen, 1 OH group. Yes, these 2 are different. And this is an ethyl group. This is also ethyl group. They are same. They are same. This carbon is not a chiral carbon. Therefore, this molecule is not a chiral molecule. It is a chiral molecule. It's an achiral molecule. Is it clear, student? Is it clear? Any doubt?
Clear, sir.
Yeah. Then see this third one. Similarly, here also a pair of compounds are given. We need to identify which one is chiral. Okay, first let me focus on this molecule. See, here we have CH2 cannot be chiral. Okay, because two hydrogen atoms are same, right? So it cannot be chiral. This cannot be chiral. This cannot be chiral. This cannot be chiral. So none of the carbon atoms are chiral carbon atoms. Therefore, this molecule, okay, this molecule cannot be chiral. It should be achiral. It should be achiral. What about this? This carbon has 3 hydrogen, so this carbon cannot be chiral. This carbon has 2 hydrogen, it cannot be chiral. Similarly, this terminal carbon, methyl group, which also has 3 hydrogen, it cannot be chiral. Now let me focus on this carbon. In this carbon, we have a methyl group, 1 bromine atom, 1 ethyl group, and 1 hydrogen. Okay, if you want, you can show this hydrogen separately like this hydrogen. So that is different. Now check all the 4 groups. Yes, all the 4 groups are different. Therefore, this carbon is a chiral carbon. So this molecule is a chiral molecule. Okay, students, turn on your camera. All of you. Yeah. So this is how you must identify whether a molecule is chiral or achiral. Okay, based on the chiral atoms present. Okay, so here we have chiral carbon. So whether chiral carbon present or not, based on that you can easily identify. Okay, right. Now we'll continue our discussion on chirality. So I have already discussed what is meant by plane polarized light. Okay, we have discussed already plane polarized light. Okay, what is plane polarized light? Plane polarized light is nothing but plane polarized light is one in which the electric field oscillate only in one possible plane, only in one plane. I'm sorry. Okay, ordinary light, when ordinary light travels, okay, the electric field and the magnetic field, they oscillate in all possible planes. Okay, whereas in plane polarized light, when plane polarized light, okay, propagate in a particular direction, then the electric field or the magnetic field, they oscillate only in one plane. That's the meaning. It will oscillate only in one plane. This is called plane polarized light. Right? When we can call a molecule as optically active, when we can call a molecule as optically active is actually an experimental one. If a molecule rotates the plane polarized light, okay, it just pass plane polarized light through some molecules. Okay, the molecule may present in solution form or pure liquid form, whatever it is. Just pass the plane polarized light through the molecules. If the plane molecule rotate the plane polarized light, if molecule rotates the plane polarized light, if molecule rotates the plane polarized light, then we can say that the molecule is optically active. So optically active is purely an experimental one. Okay, only through experiment you can say whether a molecule is optically active or not. Not just by seeing the molecule on a paper. Right? If you see some molecule on a paper, you should not say that this molecule is optically active. No, that's wrong. Only through experiment you can identify whether a molecule is optically active or not. Okay, then the next important point is this. What is meant by okay, if a molecule is optically active, it may rotate the light in clockwise or it may rotate the light in anti-clockwise. If it rotates the light in clockwise, then we call the molecule as dextrorotatory. What is meant by a dextrorotatory molecule? Dextrorotatory means it rotates the plane polarized light in clockwise. It rotates the plane polarized light in clockwise. Okay, so if a molecule rotates the plane polarized light in clockwise direction, we call that molecule as dextrorotatory. What is meant by levorotatory? L-A-E-V-O. See the spelling, students, carefully. L-A-E-V-O, levorotatory. Students, turn on your camera. Turn on your camera. Everyone, turn on your camera. Yes. Others, turn on your camera. Yeah. Levorotatory. Listen, what is levorotatory? If a molecule rotates the plane polarized light in anti-clockwise direction, we call that molecule as levorotatory. Okay, so keep all these points in mind. Plane polarized light means when plane polarized light propagate in a direction, then the electric field will oscillate only in one possible plane. Okay, whereas in ordinary light, electric field oscillate in all possible planes, right? Then what is meant by optically active molecule? If a molecule rotates the plane polarized light, then we can call the molecule as optically active. Okay, if the molecule rotates the plane polarized light in clockwise, we call the molecule as dextrorotatory molecule. If the molecule rotates the plane polarized light in anti-clockwise direction, it is called levorotatory molecule. Okay, then next important point is chiral molecule. Chiral molecule. What is meant by chiral molecule? When we can say a molecule as chiral molecule, very simple. Suppose I'll give some molecule A, okay, or some molecule, okay, I'll give some molecule, right? Take the mirror image of the molecule. Take the mirror image. Take the mirror image of the molecule. Then check whether the original structure of the molecule, okay, superimpose or non-superimpose on the mirror image. If the molecule structure and its mirror image structure are non-superimposable, then we call the molecule as chiral molecule. Okay, students, observe carefully. Turn on your camera. I'm repeating this again and again. What is meant by chiral molecule? If a molecule and its mirror image are non-superimposable, right? If these two are non-superimposable, don't write impossible, okay? See the spelling, impossible. If a molecule and its mirror image are non-superimposable, then we call that molecule as chiral molecule. Okay, and remember, all optically active molecules must be chiral molecules. Let me write here. All optically active molecules, right, must be chiral molecules. Must be chiral molecules. But the reverse is not true, which means all chiral molecules, okay, need not be optically active. Why I am saying this? Because some molecule, some chiral molecule, they rotate light in extremely small extent, very, very small extent, okay, which the instrument cannot detect. Okay, due to small angle of rotation, the instrument may not detect the angle of rotation. So we say that the molecule is optically inactive, but the molecule is chiral. Okay, so this is the point you should keep in mind. All chiral molecules need not be optically active. Need not be optically active. This is the point you should keep in mind. All optically active molecules must be chiral, no doubt in that. But all chiral molecules need not be optically active, because optically active word, right, it is related with the experiment. Only through experiment you can say whether it is optically active, whether a molecule is optically active or not just by seeing the structure. Okay, students, is this clear? Any doubt up to this? Any doubt, students?
No, sir.
Okay, right. So now you know what is plane polarized light, what is optically active molecule, what is meant by dextrorotatory, levorotatory, what is chiral molecule, and keep this condition in mind. Now, this is another point you should keep in mind. This also I told you in the last class, that is chiral carbon, okay, or asymmetric carbon. What is meant by that? Chiral carbon or asymmetric carbon. What is meant by that? Chiral carbon means, suppose in a molecule, see, a molecule may contain one carbon or more than one carbon. Okay, you just see the four atoms or groups attached to the carbon. Okay, because you know carbon valence is 4, so there should be 4 atoms or 4 groups should be attached. If the groups attached to a carbon, if all the groups are different, okay, if all the 4 groups are different, then we call that carbon as chiral carbon. Chiral carbon is usually represented with this asterisk symbol like that. Okay, so what is a chiral carbon? A carbon connected with 4 different groups. Okay, it is called chiral carbon or asymmetric carbon. And here one important point you should keep in mind, that this already I told you, whenever a molecule contains single chiral carbon, okay, molecule, students, one second. Yeah. Whenever molecule, okay, molecule containing single chiral carbon atom or only one chiral carbon atom, only one chiral carbon, molecule containing only one chiral carbon, okay, must be a chiral molecule. Very, very important. The molecule must be chiral. But when molecule contain more than one chiral carbon, okay, molecule containing more than one chiral carbon, okay, need not be chiral molecules. Okay, need not be a chiral molecule. Very, very important. Keep this in mind. If molecule contains single chiral carbon, okay, blindly you can say that the molecule must be chiral, right? Whereas if a molecule contains more than one chiral carbon, 2, 3, 4, etc., then you should be little careful. Okay, here also we have some routes to identify Okay, we'll discuss that, but this is very essential point. If molecule contain more than one chiral carbon, okay, you should look upon some other points, and based on that you have to say whether the molecule is chiral or not. You cannot say directly. Okay, yeah. So this is regarding chiral carbon, right? So what is chiral carbon? If all the 4 groups attached to a carbon are different, we call that carbon as chiral carbon, or also called asymmetric carbon. Okay, asymmetric carbon, right? And if a molecule contains only one chiral carbon, the molecule must be chiral molecule. Students, by seeing the structure, we can say only whether molecule is chiral molecule or not. We cannot say whether the molecule is optically active or not. Why? I told you optical activity is purely experimental one. Only through experiment you can say whether molecule is optically active or not. Okay, yeah. So keep this in mind. This is very important. Now let me move to the next one. This is also I have told you regarding enantiomers. What are enantiomers? Enantiomers What are enantiomers? Enantiomers, see, suppose I'll take a molecule, right? I'll take a molecule, okay. Through experiment I'll find out whether the molecule rotates the plane polarized light in clockwise or anti-clockwise. Suppose if the molecule rotates the plane polarized light in clockwise direction, suppose. Now listen, the mirror image of this molecule, right? I'll take the mirror image. The mirror image molecule, okay, also exists. Okay, see, you have taken a molecule and you have drawn some mirror image, but keep this in mind, this mirror image molecule also exists. That's the point. What this molecule will do, this mirror image molecule, okay, or this molecule will rotate the we call this molecule as an isomer. If this is original molecule, if the mirror image molecule also exists, I told you, okay, then that mirror image molecule or that structure is called an isomer. Okay, what is the difference? The difference is that that molecule and the mirror image molecule, okay, they have all properties common. They differ only in the direction of rotation of plane polarized light. So the mirror image molecule, right, this mirror image molecule rotates the plane polarized light in anti-clockwise direction. Okay, right? See, I have told you, suppose I'll take a molecule like this. See, I'll just show the flying wedge representation, which is somewhat comfortable with us. Okay, here I'll put OH group, here I'll put hydrogen, some other group, say COH. This is nothing but lactic acid. Okay, lactic acid. Now let me draw the mirror image. Okay, mirror image of lactic acid. Let me draw like this. So this group, this methyl group will reflect here, and these two group will reflect to this side. OH and COH. Okay, now see, this molecule exists. Suppose if this molecule rotates the plane polarized light in clockwise, then the mirror image molecule also exists in nature, right? And this mirror image molecule, okay, will rotate the plane polarized light in anti-clockwise direction. Okay, apart from this difference, all other properties are same for these two isomers. That's why we call the isomers as enantiomers. These isomers are called as enantiomers. So what are enantiomers? Enantiomers, let me write here, enantiomers, I'll write simply E means enantiomers here. Enantiomers are optical isomers. They rotate light. So enantiomers are optical isomers. Enantiomers are optical isomers having non-superimposable okay, mirror image relationship. Okay, having enantiomers are optical isomers having non-superimposable object and mirror image relationship. Object and mirror image relationship. Okay, one isomer is exactly the mirror image of the other isomer. I repeat, they are optical isomers, right? Suppose I have two isomers, right? Two isomers which are optically active. One is the mirror image of the other, but they are non-superimposable. That's the point. They have object and mirror image relationship, but they are non-superimposable. We call those optical isomers as enantiomers. Okay, so what are enantiomers? Enantiomers are optical isomers having non-superimposable object and mirror image relationship. Okay, right? So suppose if I give two compounds, right? If I ask you to find whether they are enantiomers or not, what will you do? If I give two compounds, if I ask you to identify whether the two compounds are enantiomers or not, what we have to do? Simple. See, first of all, you should see whether the two compounds are isomers or not. Then see the structure of the compound. Okay, and see the IUPAC name. Right. So what you have to do? See, first check whether the two compounds are isomers or not. Yes, they are isomers. Second one, see the IUPAC name. IUPAC name should be same for both the compounds. Okay, IUPAC name should be same. Okay, if IUPAC name same means they are structurally they are same. Structurally they are same. Okay, then third one. Okay, check whether the molecules are chiral molecules or not. Okay, check the molecules are chiral molecules or not. Yes, they are chiral molecules. Chiral molecules means they rotate plane polarized light. Chiral molecules means they rotate plane polarized light. Okay, so they should be isomers. They should have same IUPAC name. They should be chiral molecules. Then fourth one, they should have all properties same, all physical chemical properties same, right? All physical and chemical properties, all physical and chemical properties, they are also same. Okay, what is the difference?
Sir,
Yes,
sir, what is the difference between chiral molecule and enantiomers?
okay. Students, only chiral molecules. Okay, if you have two chiral molecules, suppose if you have two chiral molecules and if they have non-superimposable object and mirror image relationship, I repeat, suppose if I give two chiral molecules, okay, one molecule exactly looks like the mirror image of the other molecule, suppose, and if they are non-superimposable, then we call those two chiral molecules as enantiomers. Enantiomer is a pair containing two chiral molecules. Is it clear? But the two chiral molecules, right, they are supposed to be isomers. They should have same IUPAC name. Then they must be chiral molecules. Then all physical and chemical properties should be same. Right? What is the difference? The only difference is this. Okay, one isomer rotates the plane polarized light in clockwise. The other isomer rotates the plane polarized light in anti-clockwise with the same extent of rotation. What is the extent of rotation? Suppose if it rotates plane polarized clockwise by 50 degree, plus 50 degree, then this molecule will rotate the light exactly 50 degree but in the opposite side, minus 50. The extent of rotation also same. They not only rotate in opposite direction, the extent of rotation is also same. That is very, very important. Is this clear, student?
Isn't that for chiral molecules also, sir? The fifth one.
Pardon? Pardon?
Isn't the fifth one for chiral molecules also, sir?
Yes, chiral molecules. Okay, see, you have taken two chiral molecule, right? Two chiral molecule. Both the molecules should have same physical, same chemical properties. Both molecules should have same physical, same chemical properties. They should be isomers. They should have they should have same IUPAC name. Okay, if all these conditions satisfied, then you check this one. Okay, if one rotates the light in clockwise, the other one rotate in anti-clockwise with the same extent, then we can call those two molecules, two chiral molecules, as enantiomers. Enantiomers are basically isomers. Okay, they are optical isomers, very specifically saying. Is this clear, student? Any doubt?
Yes, sir.
Yeah.
It's clear, sir.
Yes, take it. Enantiomers are optical isomers having non-superimposable object and mirror image relationship. What's the meaning? One isomer is the exact mirror image of the other isomer, but they are non-superimposable. And enantiomers should satisfy these conditions. Okay, they should be chiral molecules, they are isomers, IUPAC name should be same, all physical chemical properties are same. They differ only in this. They differ only in this. Okay, one rotates the light in clockwise, the other one rotates the light in anti-clockwise. Okay, yeah. Then, so enantiomers always exist as pairs. Right? Enantiomer means pairs. Right? Now listen, students. Suppose, okay, so this is regarding enantiomers. Right? Now, let me use the next important term. What is called diastereomers. What are called diastereomers? Diastereomers. Suppose I'll take two chiral molecules. Students, observe carefully. Diastereomers. So I'll take two chiral molecules. They are also chiral molecules basically. Very important. Diastereomers can be chiral molecule. It can also be achiral molecule. It can also be achiral molecule. It need not be chiral. Okay, that's the point. Diastereomers need not be chiral. Okay, it can be chiral or achiral. Both are allowed. But this is very, very essential. Okay, they are not. They are simply stereoisomers. They are. We should not say that they are optical isomers. Okay, they are stereoisomers. They are stereoisomers, meaning they can be optical isomers. They may rotate light. Okay, they can be geometrical isomers. Cis-trans isomers. Okay, they can be of any type. But I have told you under enantiomer I told you enantiomers should be optical isomers. Whereas for diastereomers, they can be optical isomers or they can be geometrical isomers. Cis-trans isomers are geometrical isomers. You know very well. Okay. What is the difference? The difference is this. They do not have mirror image relationship. Okay, they do not have mirror image relationship. Mirror image relationship. What is meant by that? One compound or one molecule is not the mirror image of the other. They do not have mirror image relationship at all. Okay, they do not have mirror image relationship. What about enantiomers? I have told you in enantiomers the two are having mirror image relationship but non-superimposable. But here they are not having any mirror image relationship. Okay, and we call those isomers as diastereomers. Okay, and remember diastereomers can be a chiral molecule, can also be an achiral molecule. Diastereomers can be optical isomers or geometrical isomers. But this is very, very essential. They do not have mirror image relationship at all. And next important one, okay, physical properties, right? Chemical properties are different. Physical properties, okay, chemical properties. Usually physical properties are different. Okay, they may have same chemical property, but physical properties are different. That's very, very important. Okay, yeah, this is regarding diastereomers. Now let me give one example so that you can easily understand what is meant by enantiomers and what is meant by diastereomers. Okay, let me give one example. I'll take what is called tartaric acid. Very nice example actually. I'll take tartaric acid. Tartaric acid is a dicarboxylic acid having this formula CH3. I'm very sorry. COOH bond CHOH single bond CHOH COOH. This is the formula of tartaric acid. It is a dicarboxylic acid. Two carboxylic acid groups are there. And this carbon is a chiral carbon, and this carbon is also a chiral carbon. So this molecule has two chiral carbon atoms. Okay. Now, students, you know very well, whenever molecule contain n chiral carbon atom, okay, here we have two. Suppose if I take n chiral carbon atom, right? In the case of unsymmetrical molecule, let me use the word unsymmetrical. I'll tell you what's the meaning of this. In unsymmetrical molecule, right? If you have n chiral carbon atoms, then how many optical isomers possible? Number of optical isomers. How many optical isomers possible? Number of optical isomers equal to 2 power n. This is the formula we use, where n is the number of chiral carbon. Chiral carbon atoms. Take down. Okay. In the case of unsymmetrical molecule, right? So here, this is not an unsymmetrical molecule. This is symmetrical. Okay, so we have two chiral carbon. So if I put 2 here, 2 power 2, we expect 4 isomers. Okay, we expect 4 isomers. But students, observe carefully. Suppose if you assume tartaric acid as unsymmetrical molecule, suppose, then we expect 4 isomers actually. But tartaric acid is not unsymmetrical, it is symmetrical. What's the meaning for symmetrical? See, if I divide this molecule exactly at the middle, see this part and this part, they are one and the same, correct? Both the halves are equal, correct? Okay, so it is symmetrical, simple. In the case of symmetrical molecules, right, number of optical isomers will be less than this. In the case of symmetrical molecules. Okay, number of optical isomers should be less than 2 power n. It cannot be 2 power n. Okay, so for tartaric acid molecule, it contains 2 chiral carbon atoms, right? In the case of tartaric acid, it contains 2 chiral carbon atoms, but it has only 3 optical isomers. It has only 3 optical isomers exists in nature. It has only 3 optical isomers, not 4. Okay, it has only 3. Right? What are they? What are the 3 optical isomers? Let me give here. Students, observe this carefully. Let me give the structure of those three isomers in Fisher projection. Okay, because we have two chiral carbon, let me write in Fisher projection directly. One COH at the top, another COH at the bottom, and in one molecule I'll put H here, OH here, H here, OH here. Okay, then I'll draw another molecule here, COH, COH, I'll put OH here, H here, H here, OH here. This is another molecule. Then I'll draw another one, COOH, COOH, H, OH, H, OH. See, these are the three isomers possible or exist in the case of tartaric acid. Okay, let me take this as molecule number 1, this is molecule number 2, this is 3. All are isomers. All are isomers. Students, observe this carefully. Observe this carefully. Let me start with the structure 3 first. See, I have given the structure of the molecule in Fisher projection. Okay, it's a Fisher projection. Now, see in structure 3, listen, exactly at the middle, if I keep a mirror, okay, imagine, okay, it's an imaginary work, right? I'll keep a mirror plane here. I'll keep a mirror plane here. I'm dividing the molecule using a mirror plane, okay, and I'm keeping a mirror plane at the middle, right? If I keep a mirror plane here, what will happen? See, the one which is above, right, is exactly the mirror image of the below one, correct? Okay, see, you can divide this part exactly in equal half, correct? See, the upper part and the downward part are they are exactly same, correct? Am I right, student? Or the upper part is just a mirror image of the down one. Is it clear? Is this correct? If you take the mirror image of the upper part, you will get exactly the downward one, correct? Am I right, student? Is it clear? In a molecule, see, if you divide a molecule using a mirror plane into two equal half, we call that mirror plane, okay, or this plane, this imaginary plane is called plane of symmetry. Plane of symmetry. This is called plane of symmetry. So this third structure contains plane of symmetry. Okay, and whenever students, whenever any molecule contain plane of symmetry or center of symmetry, those molecules must be achiral. Okay, this molecule is achiral molecule. It cannot rotate light. If a molecule is achiral, it cannot rotate light. That's all. Okay, so this is an achiral molecule. This is an achiral molecule, and this molecule is called mesotartaric acid. Mesotartaric acid. Students, keep this in mind. Tartaric acid has 3 optical isomers. Okay, 3 optical isomers. But the third one, though it contains 2 chiral carbons, see, this is a chiral carbon, this is a chiral carbon. It contains 2 chiral carbon, but it is not chiral, it is achiral. Note this point, very, very important. Presence of chiral carbon is not at all important. Okay, what is important is the structure of a molecule and its mirror image structure. Those two should be non-superimposed. That is the prime condition for a molecule to be chiral. So here, though this molecule contains 2 chiral carbon atom, due to plane of symmetry, okay, this molecule becomes achiral. When I say molecule is achiral, it means it cannot rotate plane polarized light. Simple. It cannot. Okay, and this molecule is called mesotartaric acid. So students, keep this in mind. Mesotartaric acid cannot rotate the plane polarized light. Why? Why, student? Why it cannot rotate the plane pole side? Why mesotartaric acid cannot rotate the plane pole side?
It has two chiral molecules.
No. Why mesotartaric acid cannot rotate the plane pole side? Means, listen, this molecule is achiral molecule. Achiral molecule cannot rotate. That's all, simple. Why it is achiral? Why this molecule is achiral? Though it contains two chiral carbon, it is achiral molecule. Why? This molecule contains two chiral carbon, but it is achiral. Why? Due to the presence of what?
Symmetry.
Plane of symmetry. Okay, so let me write in the next page. Students, observe carefully. Mesotartaric. I'll discuss about mesotartaric acid separately. These are the points you should remember. I am giving Fisher projection for mesotartaric acid. This is mesotartaric acid. Okay, and remember, in mesotartaric acid, these are all essential points you should keep in mind. Okay, what are the points? Number one, mesotartaric acid is an achiral molecule. Achiral molecule. Achiral molecule means it cannot rotate light. So it is optically inactive. Optically inactive. It cannot rotate plane polarized light. Then, second important point. This molecule is achiral, and why it is optically inactive? Because it has plane of symmetry. Okay, it has a plane of symmetry. It has a plane of symmetry. Due to the presence of plane of symmetry, this molecule is achiral molecule. Okay, right? Then I'll give another important point here. What is that? Listen, actually speaking, see, we have plane of symmetry here, right? We have a plane, mirror image plane is there. Okay, we have plane of symmetry. Listen, this chiral carbon and this chiral carbon, if this rotates the light in clockwise, suppose, then this chiral carbon rotates the light, plane polarized light, in anti-clockwise direction to exactly same extent. If this rotates the light in clockwise by plus 30 degree, this will rotate the light exactly in the opposite direction by minus 30 degree. Therefore, they compensate. Net rotation becomes zero. Net rotation becomes, that's why it is optically inactive. It contains two chiral carbon, so it has to rotate. But why it is not rotating? Because one rotation is cancelled by the other, and both these carbon atoms are present within the same molecule. So this type of cancellation is called internal compensation. Okay, internal compensation. Why it is called internal compensation? One rotation is compensated by the another chiral carbon. Both chiral carbon are present in the same molecule. That's why it's called internal. Due to internal compensation, this molecule is optically inactive. You can say the other way, like this also, it is optically inactive. Some people may ask, so why mesotartaric acid is optically inactive? You can say, yes, it has a plane of symmetry. It has a plane of symmetry, therefore it is a chiral molecule. Or you can say the other way, yes, the molecule has two chiral carbon. Okay, due to internal compensation, the molecule is optically inactive. You can say in this way also. Okay, right. So this is regarding mesotartaric acid. Keep this in mind. Now I'll go back to the structures. So we discussed about structure 3. Now I am going to look upon structure 1 and 2. Students, observe this carefully. Structure 1 and 2. Suppose if I keep a mirror here. See, this molecule and this molecule, this is exactly the mirror image of this, correct? Structure 1 and structure 2 have mirror image relationship, am I right? See, COH. This vertical line remains as such. Here I have OH. This OH is here, and this hydrogen is reflected here. This hydrogen is here, and this OH is reflected here. So structure 1 and structure 2, they have mirror image relationship. This isomer exists, this isomer exists, this isomer also exists. All the three exist, and these two have mirror image relationship. Now you lift this structure and keep it over this, because it is a Fisher projection, so you can take like directly. So you lift the structure as such and keep it over this. Are the two superimposed? You lift the structure as such and keep it over this. Whether all the groups superimpose? Exactly. COH will superimpose, but here in the right hand side I have OH, but here I have hydrogen atom in the right hand side. So if I keep it exactly over this, okay, they do not superimpose. So that means they have object and mirror image relationship, but they are non-superimposable. Therefore, what does this indicate, students? Structure 1 and structure 2, okay, they have object and mirror image relationship, but non-superimposable. What does this indicate? Others, turn on your camera. Why you are not doing that? Students, turn on your camera. Structure 1 and structure 2, they are having a mirror image relationship, okay, but they are non-superimposable. Yes, you just lift. Listen, if it is given Fisher projection, you can check it directly. Okay, you just lift the structure and keep it over this. Here in this structure I have OH group right hand side, but here I don't have OH group here, so they do not superimpose. They are non-superimposable. That means structure 1 and structure 2 are enantiomers. Am I right? Okay, yeah. So what does this indicate? It indicates that see, structure 1 and 2, okay, they have mirror image relationship. One is the mirror image of the other, but non-superimposable. Therefore 1 and 2 are enantiomers. Okay, so we have 3 isomers for tartaric acid, 2 are enantiomers, and the one is mesotartaric acid, which is achiral. Is it clear? Now suppose I'll take enantiomers means if isomer 1 rotates the plane polarized light in clockwise, then the isomer 2 will rotate the plane polarized light in anti-clockwise to exactly same extent. Same extent means if it rotates plus 40 degree in clockwise, then this will rotate minus 40 degree in anti-clockwise. I don't know the exact value. I'm just giving you just for understanding purpose. Exact values are also there, but I'm giving you just to understand the meaning. Okay. Suppose if the isomer 1 rotate the plane polarized light in clockwise by plus 40 degree, then the isomer 2 will rotate the plane polarized light in anti-clockwise direction to exactly same extent. Suppose I have a solution. I'll have a solution which contain isomer 1 and isomer 2 of tartaric acid, okay, in equal amount. We call that as equimolar mixture. Suppose I'll take 1 and 2 in equimolar mixture. Equimolar mixture. Equimolar mixture means I'm taking these two isomers, the enantiomers, I'm taking the enantiomers in equal amount. Equimolar mixture. Will this mixture rotate plane polarized light, students? See, isomer 1 rotate light in clockwise, isomer 2 rotate light in anti-clockwise. Now I'm having a mixture. I'm having a mixture of 1 and 2 and equal amount, equimolar mixture I'm having. Now, is this mixture rotate plane polarized light or not?
No, sir.
No. Why? Compensation will occur, right? Rotation of one isomer is cancelled by the other, right?
The other rotation.
So what will be the net rotation?
0.
0. So this molecule shows net rotation. Net rotation is 0. This type of compensation, see here the compensation occur between two different molecules, right? Compensation not within one molecule. Compensation occurs between two molecules. It is called external compensation. Due to external compensation, okay, the molecule is the mixture is optically inactive. Mixture is optically inactive. Note down. Very, very important. Due to external compensation, the mixture is optically inactive. Individually, the molecule rotate plane polarized light, but we have 50% of this isomer and 50% of the other isomer. Okay, so the 50% of isomer 1 rotate the light in clockwise, and 50% of isomer 2 will rotate the light in anti-clockwise to same extent. Therefore, net rotation becomes 0, and this mixture is what we call as racemic mixture. Racemic mixture. Yes, student, can you now tell me what is racemic mixture? What is racemic mixture?
50% of the molecule show D isomer, with that 50% show L isomer.
Listen, here since we have taken tartaric acid and now you know what is 1 and 2 and all, but now we should give definition generally, right? So racemic mixture is an equimolar mixture of D and L isomers. I'll write in the next page. Take down, student. What is meant by racemic mixture? What's the definition? Racemic mixture. Racemic mixture is an equimolar. Equimolar means 50-50. An equimolar mixture of D isomer and L isomer, D isomer and L isomer of a compound. What is meant by that? What is D isomer? What is L isomer, students? Can you tell me what is D and L? Small d.
Rotates PP in clockwise.
Small d means this isomer rotate the plane polarized in clockwise. Small L means this isomer rotate the plane polarized in anti-clockwise. So they are isomers of the same compound, of a compound. See, of a compound. They are D and L isomers of a same compound. If it exists in equimolar amount, that mixture is called racemic mixture. Okay, this is a general statement, right? Racemic mixture is an equimolar mixture of D isomer and L isomer of a compound. And remember, the racemic mixture is optically inactive. Why optically inactive? Anyone? Why racemic mixture is optically inactive?
Net PPL is 0.
Okay, that's why it is optically inactive. Why?
Doesn't rotate plane polarized light.
Yeah, that is also correct. See, once again you are saying the same thing. I am asking the reason. Why it is optically inactive? I have given the point. No, due to what?
External compensation.
Due to external compensation. External compensation means the rotation of one isomer is compensated or cancelled by the rotation of the other isomer. This is called external due to external compensation, racemic mixture is optically inactive. Okay, so what is racemic mixture? Another question. What is racemic mixture? Any idea? What is racemic mixture? Yeah, Tejasvi.
Racemic mixture is a mixture in which equimolar D isomer and L isomer are present.
You can say simply 50% D isomer and 50% L isomer if it present as a mixture. This is very important. You should say of a compound, because you should not take D isomer of one compound and L isomer of another compound. Correct? That becomes meaningless. D and L isomer of the same compound, if it exists as equimolar mixture, we call that mixture as racemic mixture. And racemic mixture is optically inactive due to external compensation. Okay? Yeah. Now, so keep this one in mind. Next point. Next point. Suppose if I give a racemic mixture, see, I'll give racemic mixture. So this mixture is a racemic mixture. Okay, what is racemic mixture? Racemic mixture means I have 50% of D isomer, right, and 50% of L isomer. Okay, it is called racemic mixture. Now what I'm going to do, I'm going to, by using some technique, I'm going to separate the D and L isomers. Okay, so this separation is what we call as resolution. Resolution means it is the separation of D and L isomers from a racemic mixture. Okay, resolution means, okay, separation of D and L isomers from a racemic mixture. It is really a tough task. Okay, it is not that easy methods. Okay, see, on paper we can write easily, but while separating these two isomers practically is a really tough task. Okay, but for your level this is sufficient. Okay, what is mean by resolution? Resolution means it is the separation of D and L isomers, okay, from a racemic mixture. You take a mixture, from that you separate D and L isomers. This is called resolution. Okay, students, any doubt after this?
No, sir.
Good. Now let me give one more point here. This is very, very essential. Then I stop. Students, suppose I'll take a compound. Okay, a compound which is chiral compound. It's a chiral molecule. And this compound usually has two isomers. One is D isomer, the other one is L isomer. Okay, I'll take a compound which is a chiral molecule. So that compound has two possible isomers, D and L. This D isomer and the L isomer are represented by certain have different configuration. Okay, D isomer and L isomers have different configuration. They have different configuration. There is a method available to find the configuration, but we will not go into that. Okay, a compound, if it is a chiral molecule, then two isomers possible, D and L. Sometimes meso also possible, but generally two isomers, D and L. the D isomer and L isomers, they have different configuration. These configurations, okay, right, these configurations are represented by certain symbols. Okay, the configurations you can identify using these rules. Con, I'm not going to discuss anything about this. Con, Ingold, Pralag rule is there. Using Con, Ingold, Pralag rule, shortly people say CIP rule. CIP rule. Using this rule, you can find the symbol for that configuration. We have symbols. Okay, we give two symbols usually. Symbols R and S. Okay, we will give R symbol or S symbol, okay, for the configuration. D isomer may have R configuration or S configuration. L isomer also may have R configuration or S isomers. But for a compound, if a D isomer has S configuration, suppose, then L isomer must have R configuration. They have different configuration. I repeat, for a compound, if D isomer has suppose R configuration, L isomer must have S configuration. Okay, so keep this point in mind. What is meant by inversion of configuration? Sometimes people say inversion of configuration. What is the meaning? Okay, if R configuration of a molecule, okay, becomes S configuration, it is called inversion of configuration. Okay, this molecule having R configuration may rotate the light in plane polarized light in clockwise. It may. We cannot say whether it rotates, because optical activity is purely experimental one. Molecule having R configuration, if it rotate plane polarized light in clockwise, then for the same compound, the molecule having S configuration will rotate the plane polarized light in anti-clockwise. Keep that in mind, very, very important. I am not saying that R configuration always rotate the plane polarized in clockwise. No, I am not saying like that. Suppose if molecule having R configuration rotates the plane polarized in clockwise, then for the same compound, the molecule having S configuration will rotate the plane polarized in anti-clockwise. Is this clear, student? Any doubt? Okay, this is the meaning for inversion of configuration. Inversion of configuration. Inversion of configuration means, okay, R become S or S become R. That's the meaning for inversion of configuration. In some reaction, we are going to discuss. In some reaction, inversion of configuration may occur. Okay, what is meant by retention of configuration? I'm sorry, I made a small mistake here. Students, observe this carefully. Inversion of configuration in chemical reactions. R configuration become S configuration. It is called inversion of configuration. But these two are not isomers in chemical reaction. In chemical reaction, you should be little careful whether you have to check whether the two are isomers or not. Okay, it may be a different molecule also. So you need not worry about this point. This is not essential. This is very, very important. Inversion of configuration, okay, means R become S or S become R. That's the meaning for inversion of configuration. Okay, the R and S may be isomers or may not. They may be isomers or may not. Okay, is this clear, student? Any doubt? Right. What is the retention of configuration? Suppose in a chemical reaction, one molecule or your reactant has R configuration, and if the product also has R configuration, in a reaction, if the reactant has R configuration and if the product also has same R configuration, we call that type of reaction as a retention of configuration. Retention means configuration remains same. Inversion means configuration is changed, R to S or S to R. Okay, but in chemical reaction, keep this in, student, very important, are these two may be isomers or may not be. It depends upon the reaction. Okay, so you should be a little careful here. Right? Is this clear, student? Any doubt?
No, sir.
Last point. This is very, very important, student. There is no relation. There is no relation between configurations that is you say R configuration and S configuration, or no, there is no relation between configurations and the direction of rotation of plane polarized light and the direction of rotation of plane polarized light. There is no connection. Very, very important. Okay, some people they get some confusion. Okay, they say that this molecule has R configuration, and they say that they to rotate plane polarized light in clockwise. No, we cannot give any relation like that. We don't have actually. Okay, so there is no relation between configurations and direction of rotation. Right? Keep this in mind. You should not say that R configuration rotate the light in clockwise. No, it's wrong. R can rotate the light in clockwise or anti-clockwise. It depends upon the molecule. Is this clear, student? Any doubt? Yeah, we have discussed.
No,
Yeah, good. We have discussed the concept which is required for haloalkane and haloarenes. Okay, from next class onwards, we'll start the actual chemical method of synthesis. That is preparation of haloalkanes and properties of haloalkanes. We'll discuss from next class onwards. Okay, yeah, I stop here.